Hello everyone, welcome back. This is Professor L. Last time we talked about structure. First, we had to draw a couple possible isomers in Lewis structure. For example, you put the multivalent atoms in certain random order. Then you must connect them with at least one sigma bond. Then you add their valence electron in neutral state first. Depends on the given formula, their formal charge. Then carbon should have 4 electrons, so here one in the sigma bond and second, third and fourth. Nitrogen 1, 2, 3, 4 and the 5. Then say if you have a hydrogen given, then you add one hydrogen with a 1 electron up to the max for each atom. For carbon, since it's a second row element, 8 total is the maximum. So here you have 8 electrons. Then nitrogen can have 8, and you have 6 for now. So you can add up to 2 more, depends on the given number of hydrogen you have. If you happen to have one more hydrogen given, then it cannot be H neutral, because then nitrogen must have 9 electrons. That could be too repulsive and too high potential energy. So you must add H plus. That makes the molecule overall positive. But then you wonder what charge you must give to which atom. Then you count its own electron number. Say hydrogen must have a 1 electron, and there these two are shared, but only one. Say this one belongs to hydrogen, then the other one belongs to the nitrogen. Likewise, you count the number of electron for nitrogen, and you find 1, 2, 3, 4. When the neutral nitrogen must be 5 electron on the valence shell, so you see the nitrogen lost electron, and it lost electron when it make a bond with the H plus. Instead of taking one, it gave both to the hydrogen and shared, but at the end you have one for you and one for the hydrogen, so you have actually given one to the hydrogen. Therefore the nitrogen should have a formal charge. Without using formula, you can actually calculate the formal charge this way, and you can see the carbon must have a 4 electron of its own in the neutral state, and you see 1, 2, 3, 4 belongs to the carbon, and each one here, there belongs to each hydrogens here, and same for these, so they are all neutral. So this positive charge is actually from the nitrogen. So the Lewis structure is completed, and we can also use regular line to represent pair of electron. So the structure is flat, it has no three-dimensional information. Then we can apply potential energy concept by using VSEPR, valence shell electron pair repulsion theory. Then we know that the carbon with the 4 pairs of electron in the sigma, same for the nitrogen, should have a tetrahedral arrangement of the electron pairs, and all of the pairs are bound to the atoms, so you can actually have a tetrahedral shape, unlike oxygen we had in the previous video. So there you can have tetrahedrocarbon drawn this way. Then you can connect nitrogen, say, over here. Then the rest of the arms are hydrogens. Then this nitrogen, which is this guy, is positive. Then you should have another solid line. You can do it any way, but you know, when you have a same type of a group, you want to have a staggered confirmation. So I would draw the solid line opposite to this, which is here, and giving 109.5 degree angle right there. So having these two lines, you know, you have just option to have the line coming out and in, representing hydrogens pointing in and out. So that's your Vesper. There you have the model for this molecule. The blue ball represent carbon, and these are the hydrogen. I didn't put white balls. And the blue ball for the nitrogen, and there are 3 hydrogens, and this is the Vesper structure. And you can call that as wedge and dash structure. And you can see this molecule from different perspectives. Depends on the needs. Sometimes you need to see the Newman projection this way. Then you can observe how close these groups or these. So this is a staggered, and the eclipsed here would be having closer electron pairs, thus it has higher unstable potential energy. When you have to draw them out, you can assume that you can looking at the molecule downward or upward to have the 2 atoms overlapped with the sigma bond in between. Say you are looking at this molecule from the top. Then this circle represents the carbon. Then you have this hydrogen on top, and these 2, like this one over here and that one right there. Then behind you have a nitrogen that's positively charged, and we don't see them, and that has 2 hydrogens going up, and this pointing out one, which is this one. When you turn this molecule this way, as you see, that's located right here. Try that again. This one pointing out, not the pointing in one. This one, when you turn to have the perspective from this angle here, so your eye is here, like the camera right now. If you turn, eye is right there, like here. So that hydrogen goes there, and this hydrogen represents the one behind, and this one. So when you flip this drawing this way, you would get this drawing. From this side of the perspective, you see this molecule just like that. I'm sorry, it should be this side of the perspective. Then you would get the carbon here, nitrogen there. Sorry about that. So that one has lower potential as staggered. If you want to have the eclipsed conformation, then you would have to turn around single bond by moving front carbon or the atom behind. In this case is nitrogen, so everything moves this way. So you do that by 60 degree, and the front carbon with the 3 hydrogen is still there, and this hydrogen move up here, that moves down there. That's 60 degree from here, and this one goes here. So you have eclipsed, and that has a high potential energy, and you need to force them. However, in a given temperature, it might be able to travel. The difference is only a couple kilocalorie per mole, so that's quite doable at room temperature, meaning the rotation is freely happening. Then we did Fischer projection. Newman, then Fischer, with some degree of distortion. So we said the Fischer cannot be drawn from this perspective. That's because the lines that goes to the top and the bottom but around the nitrogen it goes up outward, and the bottom one comes outward, so you cannot draw the Fischer projection right now. So you have to have eclipsed away, as you see. Also, you should have the top and the bottom lines going away from you. Then you can imagine flatten out like this. Okay, I need to distort more to show you the bottom line. Then you can copy this, and that looks something like this. So in the center here you have a carbon, and you have a parallel line here in the middle, and there's a nitrogen, and you have two parallel lines. Then this line going away, you just show solid line, and the line here on top also going away from you, but in the Fischer projection you just show it like that, and all of them are hydrogen. Or you can draw it like this. You can simply say these are going away and these are coming at you, so you can put these on the parallel side. In the middle you have a carbon, and this line is hydrogen going away from you, and these are hydrogens, and this line is going away from you, so you can put NH3 positive. That's another possible Fischer projection. Then you have to freely convert this Fischer to the Newman projection. You have to practice. So for that, you have to imagine this being going away and these coming out and going away. So there's a carbon, like just like this. So if you position right around here, if you turn, you see from this angle you can have nitrogen and carbon overlapped. From the top it may look like it and having your eye here, but your eye actually see it like this from this angle, right? So then you have circle, then two hydrogens here and there, the third one here, and that is your nitrogen positive, and you have eclipsed 3 hydrogens on the carbon, there you have Newman projection, and that's not stable, so you have to turn to make it staggered. That's where we stopped. Alright, let's practice with these 3 different drawings: Newman, wedge and dash, and the Fischer. Can you see any similarity? Let's see. The first Newman projection is drawn when the molecule here is held this way. Try to catch all the features. Okay, so I have these 2 atoms right here, these 2 atoms and the middle bond overlapped, and they are staggered, and that is shown here as a Newman projection. And the rest, as you see, the front carbon is holding the blue ball, represented as a B here. Then hydrogen, I didn't show here, excuse me, hydrogen. Then you have a CH3 here, I'm holding it by. Then in behind, the carbon is holding blue ball here, the yellow ball there, and the red ball here. Look at the actual structure. So right here, I'm putting it down. Then the next one is this one right here from this angle. Okay, so you have the carbon here holding, excuse me, I have to turn, holding the yellow ball up here, red ball here, the blue ball here. Even when it's drawn the original way I was holding, you know, you can always turn, because I didn't change anything. It's the same molecule, it's just different conformation. So it's allowed it. Then the second carbon here, which is this one, holding blue ball coming at you, and the other hydrogen that's going away from you. Then I'm holding the whole molecule by CH3, which is here. Also, the last one, it is this molecule, but it doesn't look like same. Be careful. You have CH3 right here, going to the top, blue ball here, hydrogen here. Then the second carbon is right here, then the blue here, but it's red, red here, but it's blue, yellow is here. But what's wrong with this? This is not the way you draw Fischer, or that's not how you imagine the Fischer to the real molecule, because the Y here, the yellow ball, must be going away from you when you are putting anything on the vertical line. The method was okay, it's going away from you. However, the yellow is not, so you have to turn the yellow ball away from you. Then it is going away. That makes the blue ball come back where it should be, and then the red ball coming here. So this is the molecule there, and that was the same molecule that is shown by this drawing here. It's exactly same thing, except that you have to turn. So they are exactly same. How about this molecule, which is this, and this? Let's compare. When I put it down, try to match. As you see, they're perfect match. So they are all identical molecules. Also, for the Newman projection, besides the name Staggered Confirmation and Eclipsed Confirmation, you need to learn a couple more namings. You have many ways of having staggered, like this, or like that, or even like this. So in each confirmation, you have a different relationship between these groups and this group. So you can say that in this confirmation, the blue ball is anti to this blue ball, meaning they are in opposite direction. Then you can say the blue ball is in gauche to this red ball and this yellow ball. Or the yellow ball here is the gauche to the blue ball here. Same for the red. So anti-staggered and gauche staggered. When something is anti, that can be more stable or even less stable. Let's say the blue and the blue has same charge, such as methyl group and the ethyl group, some CH3 or C2H5, same kind of nature group, then they would repel with the same kind of charge. So it's better to have them apart. If you bring closer, then the distance decreased between the same charge, so the potential energy increase in gauche form, that wouldn't be stable. So they prefer anti to gain more distance. However, if the blue was negatively charged group and red was positively charged group, then the anti between these two groups is not necessarily stable because you have an opposite charge apart. To lower the potential energy, you have to bring the opposite charge close, like a gauche. So the gauche can be more stable. If you have eclipsed, then you have a more complicated situation. Although you get the closer distance between these two opposite groups, you brought all these 6 pairs of electron in bonding too close. So that might be too much. So it all depends on how much repulsions you have between 6 electron pairs in the sigma bonds and how much attraction you have in these two opposite charge groups. So for example, these two are exactly the same compound, butane. You can see the 4 carbons, 2 and then 2 here and behind. And you look at them, you find the difference. The same kind of groups are apart here, but there you have them closer in gauche. So is anti more stable or gauche more stable? Obviously the same charge group repel, so the anti would be preferred. It's more stable confirmation. Here you have another example, and I built the model. these two carbons are eclipsed to show you the Newman perspective. Then in front carbon you have fluorine, and behind carbon you have OH right here, and they are in the anti-conformation, anti-position in this staggered conformation. And there you have another staggered conformation, but you have a OH in front. So you can see the molecules can be drawn from different perspectives. So you have to practice looking at them from different perspectives. I don't recommend you to redraw them. If you have to, you do, but it's better imagining molecule like this in your head and trying to flip from this given molecule, imagining this kind of virtual mental model, and you flip and it still doesn't match, then you turn. Then you match the oxygen and 2 hydrogen in front, but fluorine is not there but here, so you have to twist. All of these motions are allowed in natural state because single bond can be rotated. Then you have the fluorine next to the OH, so you have a gauche conformation. Which is more stable? Remember, fluorine is more electronegative than the carbon, so it has partial negative. Then oxygen is more electronegative than carbon and hydrogen, so you have positive charge on the hydrogen. Then these can have a strong hydrogen bonding in gauche, not in anti. So the opposite charge stabilizes each other by forming hydrogen bond. Therefore, gauche conformation happens to be lower energy than anti. So this is more stable conformation. Okay, let's talk briefly about how to form and draw cyclic structure. In order to form a ring, you at least need 3 carbons or 3 atoms. So as you see here, I have 3 carbons with a bunch of hydrogens, and you can bring the 2 end carbons to form a bond, but as you can see, without distorting natural sp3 tetrahedral geometry, you cannot form. So I have to force them, and as you also can see, it's not easy. And I've done it. And the bonds, I hope you can see it, it's not straight, they're bent. Then when you try to see it in the Newman projection, you turn, overlap the 2, then you can notice these are all eclipsed. So very unstable repulsion by electron pairs. Also, the sigma bonds are not stable. Now I have 4 carbons. When I try to form a ring, I don't have to force as much as I did for 3-membered ring, but I still have to force. And the bonds are not as much bent, but they're still bent a little bit. Also, the angle here is 90 degree-ish, not 109. The triangle had 60 degree, far from 109. That means you had to compress these bonds away from natural 109 and closer and closer to achieve a 90 degree in this case. So much repulsion. On top of that, if I show the Newman projection, the one circle representing the 2 here, and the other circle representing 2 there. They are bound together this way, and they're all eclipsed. Very unstable as well. To help your understanding, I drew Newman projections of the 2 cyclic structure, cyclopropane and cyclobutane. And the cyclobutane has a little bit of flexibility, so they can release slight angle and the ring strain by bending it. So it's not any more perfect square, it's a slightly twisted. I hope you can see it's not linear anymore, it's kind of bent. So when you see it as a Newman projection, they're not perfectly eclipsed and they're not perfectly staggered, but it's better than eclipsed. Everything here. So they relieved some angle strain and ring strain. So that's how you can draw that partially better cyclobutane ring. And next I have 5 atoms. On its normal chain, it's freely spinning around single bond. But when they are forming a ring with the 5, it's not difficult anymore, it's naturally closing in to form cyclopentane, 5-membered ring. But as you see, it's not really plain, but this part is coming up from the plane over here that's formed by these 4 atoms. See, the 5th one is sticking up. Also, I can show you that these 2 carbons making the eclipsed conformation, but unlike previous 2, you have over here perfect staggered. So you can see the 5-membered ring has not much of the bent sigma bond and not much of the angle strain, because it's almost a natural tetrahedral arrangement, and there are some eclipsed partially, but there are also some staggered, so the ring is not too bad. That's why you're finding 5-membered ring in the naturally happening compound. So next you have 6 carbon trying to form bond. It's not easy though. So you have to bring the group like this, and that's kind of eclipsed, kind of, and you have to bring this one to the high energy, more eclipsed location. Then you have to move groups in an appropriate way, then you can close in. But once you close, you can see there's no angle strain, no bent sigma bonds, and see the Newman projection here, perfect staggered, and next sigma bond, if I show you, it's nearly perfect also, and next one is also perfect, and as well as this. So all the bonds are now fully staggered. So this ring is very stable, but it's more difficult in taking time to form the ring. So this ring is very good and stable, but it's slow to form. And if you have to show the Newman projection, you have to hold this perfect hexagon looking one from the top, but if you see from the sideway, it's not really flat molecule. So you have to hold it in a certain way. So for Newman projection, you have them overlap this way. Then you can see these two overlaps and these two overlaps and making two circles. So two circles. Then you can see this one here is coming down from the both circle and have the hydrogen sticking out and going away from you. So coming out, going away from you. Then here you have two other hydrogens, up, down. And same for here. Then you have the CH2 over here with a one hydrogen coming towards you and the other one behind there going away from you. So you show it like this, coming at you, going away from you. Those are hydrogens. And there's another hydrogen here, which is this guy, and there's one more here, right there. There you have one Newman projection from this, and you can have different perspective to show Newman projection. Also, say I just did from here, sorry, I did it from here, but then you can see the same molecule from this angle, okay, not the one you have right now, this angle. But if you see from here, where my finger is from, let me turn. See, you can have other two circles, here and here one, and here another one. This time the CH2 is pointing up, not down. There are many different perspectives that you can show the Newman projection, but they are essentially describing same molecule. There. This is our cyclohexane with the 6 carbons. We need to learn a little more about this structure. When you turn this perfect cyclohexane hexagon, turn into this kind of shape, and we have to duplicate it. Then you have to compare this one to this one. Okay, this one. Did you see what I did? I just turned around single bond. I twisted the single bond, and other nearby carbons are twisting as well. If you do this with your own model, you can see the single bonds here and here, they are turning. Okay? So this one here, the first one I had, you can pause the video if you had to. That's what I'm trying to show you how to depict. So first I'll show you how to draw first two slanted line. It should be same size of line, separated by a bit more than the length of the carbon-carbon bond. Not too much, but a little more than 1.5, I guess. Then you split the angle here from this imaginary line here and here, and that has to be same length, and you split the angle as well here from the top imaginary line, and there you have two shapes. Then you put another parallel line to connect those two and close in a ring. That's basically the backbone of, backbone of these 6 bonds connecting carbons from this perspective right here. Then you have to add hydrogens. So before doing that, you have to know from this perspective you only see the lines like this, but in reality these 2 carbons are out of the plane. The plane made of this the plane that cuts the molecule in half, going through the middle 2 carbons here. So that imaginary plane, let me use my hand, like this plane. Okay? So these 2 are above the plane and those 2 are behind. So when you see this molecule, this perspective, you have to know these are above these 2 and those are behind of those central 2 carbons, and those 2 central carbons are this one and this one right here. So those are above and those are below, and none of these are parallel, but these are parallel to that imaginary plane that cuts the molecule in half. So this carbon here is this carbon. Then this carbon's coming at you, and this carbon here is going away from you. So I can show it like this way. I have the carbon here, which is this guy, and this line is actually coming out. That line is going away from you. So from our practice earlier for the tetrahedral, you need to have 2 solid lines that represents the lines on the plane, and they are these 2. Okay, so when you hold this parallel to you, then you have this wedged line representing this guy right here, and the wedged dashed line representing the line here behind. So you put the line this way. So we call the line going down as axial. The tilted one up is equatorial. In same manner, you have this line over here coming out and this one going in. So you can imagine one axial going up and equatorial this time going down, and they have to be 109, 109, 109, 109, perfect tetrahedral. This part. So if you practice same way, this one's a parallel solid line, So 109 from there, you can imagine axial. Then this is going away from this carbon, so you can imagine the one coming out, so you should put it right here. And this is a parallel line. Another parallel line for the tetrahedral is like this, axial. Then that one, as I explained earlier, going in, because these two carbons are above of the central carbon, so the line is going in, so you can imagine the line that's coming out here. So same manner, axial, and the line from this carbon is coming out towards us because these are behind. Then the other line left is going away from you. Then this carbon has solid line, so another solid axial going up, 109 angle you made. Then this one coming out, the behind carbon to the central carbon, so coming out, so the other one is going away from you. So there you have all the 12 hydrogens, 6 axials, three of the 6 are down, and down. Other 3 are up axials. There are 6 equatorials, 3 ups, up, then up, then up. 3 are down, alternatively. So you should be also drawing this one from different angle. Also should be able to add lines for hydrogens or attach the groups. So this way, 2 solid lines coming out, going in, coming out, going in, so 2 solid line. There, a solid parallel line, so another parallel line going in, coming out. So you keep practicing. So somehow this part of the ring resembles chair, beach chair, so they call it chair form, but especially this conformation changing to the other by turning single bond around, so we call them chair conformation. And the other one I showed you earlier was from this perspective, I push this one up. Then as you see the equatorial turn into axial, the axial turn into the equatorial, you can imagine and observe. See, that became axial, right? And then overall backbone, this angle, it looks like this. And they call it boat. And you can see the axial is not exactly axial, so pseudo-axial they call, and pseudo-equatorials, and the pseudo-axials are very close, so they repel. And these equatorial axials, let me show you from one angle. They are, see these two and these two, they're perfectly almost eclipsed. There's some staggered here and here, so partially staggered, partially eclipsed, like cyclopentane. That's the cause of instability of this conformation, and that looks like a boat. So more stable, less stable, so the energy is required. Unless you have some polar groups like this and causing some interactions to lower potential energy. Okay, so as you can feel, the So demand for the three-dimensional perspective in chemistry is getting higher and higher, and believe it or not, that is one of the main crucial factor for student to be successful in organic chemistry. So the best way of learning this is not learning some tricks, but play with the models and try to build the virtual model in your mind and be able to imagine them better and let your brain learn how to imagine these complex structure better. At any moment though, you always have to estimate the attractions and repulsions of the charges, because that's the main cause of the changes in chemistry. It's tough, yes, but everybody who put the time and effort will do it. So I hope you can keep in good spirit and push forward and be with me, and I'll help you. I'll see you next time.